and welcome back, and this is the Chipmaster, and as you know, my name is Stephen Forbes and I'm the Chief Engineer of Computer Maintenance in my department. Alright, so we're going to talk about in this video is common notebook power supply modes. As you can see here from the presentation, we have three modes, which is switch mode, right? We have LDO mode and we have PWM mode, right? So the switch mode, as you can see here, is the switch, which is the mode which is used for MOSFET or transistor conduction from standby voltage conversion after pressing the switch, right? Then we have LDO mode, which stands for low dropout regulator, and we have PWM mode, which stands for pulse width modulation, right? So we're going to look at each of these modes in detail, right? This is a demo video, right? So this is the a part of the full training videos that you will get, right? And we're going to do them step by step. So let's start, and we're going to look at the switch mode. Alright, so this mode is used to control the conduction of a MOSFET on and off, switching from standby conversion after pressing the switch to run voltage as shown. So as you know, in SLPS3 state, when you press the switch and SLPS3 is released from the CPU or the PCH, it basically comes to the gate or to turn on another MOSFET as a conversion gate to output its designated voltage. As you can see, this is acting as a switch. So this is the switch mode power supply, where we're taking a voltage from here to another source without losing the power or the current, right? The current will be the same, the voltage will be the same. There's no voltage drop and no current loss. So this is known as a switch mode power supply, right? As you can see here, so this is a MOSFET. Can anybody tell me what kind of MOSFET is this? Right, so in the electronics foundation class, you'll learn about the different types of MOSFETs, such as P and N channel MOSFETs, and working conditions of each. Alright, so as you can see here, we have here a gate, which is the G pole, and we have the S pole here, and we have the D, which is the drain. So we have gate, we have source, and we have drain, right? So as you can see, when main D comes to the gate of this MOSFET, right, the voltage at the gate, which is an N channel MOSFET, if you notice there's an arrow on pointing in, right, to the gate, that indicates this is a NPN MOSFET, right? This is an NPN MOSFET, meaning that the gate should be positive, which is the gate. So this is a positive, so voltage should be here. So once you put the voltage here, so the voltage, normally the conduction value of this MOSFET is about 4.5 volts. So once 4.5 volts or more is coming to the gate, then this MOSFET will conduct, right? So this is how the working conditions of this MOSFET. So this voltage is normally about 15 volts. Sorry, this voltage is roughly about 15 volts mainly, right? As you can see, this is a coming from a quanta board. So mainly this is normally about 15 volts coming to the gate. When 15 volts come to the gate, it will conduct. This 5 volt PCU will become plus 5 volt, right? And as you notice, the current is 5.8 ampere because this is coming from the SMPS or the standby rail, right? So this is known as your conversion circuit. So this is a switch mode, which is taking 5 volt PCU from PWM to 5 volt run. Normally this voltage will go to the hard drive, right, and other places, right, but primarily to the hard drive. All right, so this is known as a switch mode power supply. Alright, let's take a look at another power supply. This is another one using a chip to control the on and off of the secondary supply, right? This is another chip. This is a chip technique used to output another power supply. As you can see here, we have 3 volt run coming in, right, to pin number 4 and 5, right, and we have an EN, which is the turn on pin to tell the chip to start working. So as you can see, it's coming from this source. So any one of these two signals has high level, right? Any one of these two signals. This is a diode D3, which is an OR application of a diode, indicating that any voltage come on any side. This is an OR, which is known as an OR. You can use an OR gate, right? So this is an OR application of a diode, using a diode as an OR gate. And basically what will happen is that any voltage come in at any time, if this is low and this is high, it will work, and vice versa, it will output and comes to the enable pin, which is pin number 3, and then it will output, as you can see, LCD VCC, and LCD VCC supply is normally going to our screen, right? This is normally going to the screen power supply, 3.3 volts. So 3.3 volt run, and it is outputting 3.3 volts. So this is known as a switch mode power supply, using a chip to control the on and off switching of the secondary supply, also to give other power supply, other devices its power, right? So this is another technique that you can use to This is another power supply, which is a switch mode to output its voltage with the same current and voltage, no voltage drop or current loss. Alright, let's take a look at another one. So this is a circuit application of a switch MOSFET. Right, switching, as you can see, when source on is high level, so this is source on coming in, right, which is greater than 1.9 volts. As you can see, this is another transistor. This is a transistor, this is not a MOSFET. No, as you notice the symbol, right, the diagram here, which is a NPN transistor. Sorry, this is a N channel transistor. See the voltage at notice the arrow is pointing outwards. So this is a transistor. So this is the base, right, so this is the base, right, this is the collector, and this is the emitter, right. So B, C, and E. So B is equal to E, right, and C, which is going to be equal to E when it conducts, right. So B and C is connected. If you notice the diode, this is a transistor, which is a N channel transistor, and source on, which is, so once 1.9 voltage or more comes to the base of this transistor, then it will conduct, right. So if you notice the A point here, so PQ14 will conduct at the A point, right, and it will become low. As you can see, this is low, the A point. When this transistor conduct, the ground here will conduct, so here will be 0 volts because it's grounded, and at the same time it's going to cut off these MOSFET because this is an N channel MOSFET. As you can see, right, this is an N channel MOSFET. The arrow is pointing on the inside, so when A is grounded, this MOSFET is an N channel MOSFET, so the voltage at the gate, right, is same as the voltage at the source, so it will cut off. Here is the same, the voltage at the gate is the same as the voltage at the source, it will cut off. And what will happen is that we have 15 volts here coming through a 1 mega ohm resistor, which is becoming source D, and it is going to conduct 5 volt PCU to 5 volt source, and current is 2.49 volts. And this is another switch mode power supply, and the output voltage is going to power the hard drive and so forth, right. So source D, which is to 15 volts, controlling PQ11. As you can see, this is PQ11 to completely conduct, producing 5 volt source from 5 volt PCU. So this is 5 volt PCU to 5 volt source, as you can see, and it is going to power the hard drive. So this is another this is a nice application of a circuit. Once you understand how this circuit works, then you can troubleshoot. Most times in a no display fault or power down, this circuit can cause the fault. If there's any fault with these components, it can cause no display or power down, right, depending on the manufacturer of the motherboard and the configuration of the EC BIOS and configuration of the EC, right. So this voltage, this application of this switch circuit is very important to understand, right. Very simple, not complex. All right, so let's take a look at the next application. So look at the signal. This is another circuit. As you can see, we have a diode, we have a MOSFET, and another MOSFET here, and a MOSFET here, right. So if you notice these two signals, ENVDD and LCD VCC underscore TST, which is coming to D8 and D15. So this is another OR application of a diode. So whether enable VDD or LCD VCC underscore TST comes in high, then it will output, right. So any one of these signals coming high, if both of them is on, it will output and conduct Q55. Q55, as you can see, the arrow is pointing inward, so this is an N channel MOSFET, right. So the voltage at the gate, which is 1.9 volts or more, which is greater than the source, it will conduct, right, and this will be 0 volts at this point. So as you notice, this 0 volts is also coming to the gate of this MOSFET. If you notice, this MOSFET is a P channel MOSFET, the arrow is pointing outward. So what will happen that this 3 volt VS will conduct and become LCD plus LCD VDD, and this is going to power the screen again. So this is another application of you, instead of using this as an IC, now it is using the OR application of a diode and a MOSFET to switch the power, right. So you can see any signal on D18 or D15 becomes high, right, will cause Q55 to conduct, which is this one. So Q55 conduction pulling the gate of Q37. So Q37 will pull low, So when the zero voltage voltage comes to this section, the whole of this pin, which is going to pin 2 of the gate, will be low, and it will control the conduction of the screen power supply. This is a P-channel MOSFET, so the voltage at the gate should be less than the voltage at its source. So this is the source, as you can see, S, right, and this is the drain, and this is the gate. So the voltage at the gate is 0 volts, and the voltage at the source is 3 volts, so it's less. So it will do a full complete conduction without no voltage loss or current loss, and producing its power supply, which is L plus LCD VDD, to power the LCD screen. Alright, so this is another application of using an OR diode, or using the chip, anyone which is preferred, depending on the manufacturer of the engineer of the manufacturer who is designing the board. Alright, so let's move on. Alright, so we have LDO mode now. So LDO, which is low dropout regulator, right? Low dropout regulator is a voltage stabilizing component, right? A linear voltage stabilizing component, which its input and output voltage difference is very small, right? It uses a chip to output, right? There is no inductor. The output current is small, as I said before, and it uses a chip normally to output its power source. So as you can see, we have here a schematic which is taken from an ASUS. As you can see, AC underscore bat underscore 6, which is the common point rail for the ASUS architecture, and it's coming to pin number 1, and pin number 1, as you can see, is in, right? We have pin number 3, which is ENBL, which is enable. So when we get supply and we get the turn on signal to tell the chip to start work, it will output its designated voltage. As you can see, 12 volts sus, and the current is 100 milliamp, which is very small, right? Because this is a LDO mode, right? LDO mode doesn't use any switching. It just output an open drain and releases its voltage with small current to power small devices on the board, small components or other devices. So you don't need a large current, right? So as you can see, we also have 2 resistors here, which is acting as a adjustment feedback. So this is a feedback. You see ADJ, this stands for adjustment. So if the voltage is going over the 12 volts, what will happen is that the voltage on this coming through this resistor divider will be adjusted to output a designated voltage, and the formula for this is normally the VREF, which is the voltage reference, which is here. This is the reference voltage, which is 1.2 volts, right? So 1.2 volts, let me get the point of it. So 1.2 volts here is which is 1, right, plus R1. This is R1, right? 1 plus R1, right, divided by R2. That's the formula. So 1 plus R1 divided by R2 to give you the output voltage, to keep it at that voltage. So if the feedback voltage is here is abnormal, it is if 1.2 volts of this feedback voltage becomes abnormal and it is changed, the output voltage will be cut off. There will be no output. It will go into protection mode, indicating that it's either a short circuit or overcurrent protection, or an overcurrent situation happening. So the chip will stop output and basically will protect the chip and to protect the other devices from being damaged, right? So this is the feedback. So the feedback, which is 1.2 volts, which is after the voltage going through these 2 voltage dividers, these resistors, which is a voltage divider, the output, the voltage coming back to this pin should be 1.2 volts, which is the feedback adjustment, right? So it's 1. To calculate this, it's 1, right? 1 plus R1, right? This is R1 and this is R2. Let me just move this out of the way. So it's 1, alright, so it's 1 plus R1, right, divided by R2, right? So this is R1, alright, so this is R1 and this is R2, right? So this is the formula. So it's 1 plus R1 divided by R2. So doing the mathematics, you should get 12 volts here. 12 volts should be constantly going to supplying, right? And this is the feedback. So when you get the answer, you should get 12 volts after calculating the value of the resistors, 845K and 93.3K, right? and then you add that to 1, then divide it by the R2, which is 93.3, then you will get 12 volts. Alright, so let's take a look at the next one. Alright, so we have another common use LDO chip, which is used to power the RAM VTT power supply. Right, VTT stands for the voltage termination, which is the bus power supply for the RAM. Right, and this is normally half of the voltage of the RAM power supply. So as you can see here, we have 1.5 volt, which is coming in, and we have 3.3 volt, which is the working voltage. Right, these two voltage comes into this chip to form a pressure, which is going to release, and it's going to form a reset signal that is integrated inside of this chip. So 1.5 volt, which is the RAM supply, and 3.3 volt, which is coming to V control, which is the working mode power supply and the main power supply. As you can see, at the same time, this 1.5 volts is going through another voltage divider. As you can see, this is 1k. This is half of the voltage, which is going to be acting as a reference input. Right, so this is our reference input. So the voltage divider calculation is R1, right? R1 plus R2, which is divided by R2, which is multiplied by its source, and after calculating it should get 0.75 volts coming to here as the reference input, and at the same time it is an enable, so it is acting as a reference and an enable, and then it will output 0.75 volts, right? So that's it. And inside there's a thermal shutdown and an overcurrent protection also, so if there's any overcurrent happening on this line, it will stop output and go into protection mode, right? So this is another low drop out regulator, which is using a chip, and it is used in a lot of motherboards to output it the RAM termination supply, which is half of the voltage, which is 0.75 volts. Alright, let's take a look at the PWM. So pulse width modulation, PWM, right? So the pulse width modulation is a digital signal, right? The full amplitude, which is a DC power supply, right, at any given moment. So once there is a voltage current or voltage coming in at any given time, right, it generates a pulse, right? It's either completely on or non-existent, which it is off, so it forms a pulse. That is why it's called a pulse width modulation. The width basically means the time, right? The time in which how long the voltage will be there, right? So the T, it is the time on, right? So this is basically connected like a frequency ton. That is why most of the chip you see on a schematic, you see TON, ton, which is the switching frequency, how fast, how long, and how fast the MOSFET, the upper MOSFET will switch, right? So the voltage or current source is applied to the analog load in a repetitive pulse sequence, which is on or off, right? When it is on, it is when the DC power supply is added to the load, and when it is off, the power supply is disconnected. So in a typical pulse width modulation on oscilloscope, it looks like this, which is a pulse wave on and off, right? So this is on and off, right? So depending on the time, how long, as you can see, a MOSFET can switch, then it's generated as the pulse width, which is the pulse width, how long the MOSFET will switch, right? The upper MOSFET. Alright, so PWM, which is a power supply, PWM power supply composition composed of a PWM chip, a MOSFET, inductor, and filter capacitor, right? Typical PWM chip consists of a PWM chip, an upper and lower MOSFET, an inductor, and a filter capacitor, or a buck, and SMPS is also the same power supply mode, so you can also call it a buck power supply or SMPS, which as SMPS stands for switch mode power supply. Right, so this is a basic theory explanation of the PWM mode power supply, which is the most complex power supply in a laptop motherboard and a desktop. Right, understanding the pulse width modulation of a PWM circuit, which gives you maximum increase your repair rate, and how to understand how pulse width modulation circuit work. In future classes, you will learn a lot more in detail about pulse modulation circuit, how to use oscilloscope to capture different faults such as overcurrent or under voltage or overcurrent protection, right, and under voltage, right, and how to know when the chip is protected using datasheet, and all those techniques will be implemented, and I will show you all secrets about a pulse width modulation circuit. All right, so a typical PWM circuit, as you can see here, we have a chip, which is the control chip. We have two MOSFETs, an upper MOSFET and a lower MOSFET. We have a PWM, we have a coil, and we have a filter capacitor, right? The filter capacitor, which is a capacitor which is connected to ground. Any capacitor connected to ground, it becomes a filter. If it's connected to a signal, it becomes a coupling, right? So this is the PWM chip. We have a trace here which is connected to control the upper MOSFET gate, and another one here to control the lower MOSFET gate, and it is switching. So the switching, each time it switches, it creates a pulse. This is the inductance front end, and this is the inductance back end, right? So when this chip gets its working conditions, then it will start to drive, right, the upper MOSFET gate, right, and it will switch, right? As you can see, this is B plus. This is normally 19 volts coming to the drain pins of the inductor of the upper MOSFET, right? And as you can see, the source pin is of the lower MOSFET is connected to ground, right? So what happens is that each time a MOSFET conduct, you have high, low, high, low, high, low at the front end here. So what will happen that these two MOSFET switches at an interval state. These two MOSFET cannot switch at the same time. If this MOSFET switch together and this MOSFET switch at the same time, it will be a large short circuit, and it will burn the chip, and it also burn the output power supply. That is fire, right? Two MOSFETs can switch at the same time, so they switch at an interval, and that is controlled internally. There's a internal latch that's inside of the chip. When you read the data sheet, it will tell you, right, and you can use oscilloscope to know which MOSFET switch first, right? So as you can see, we have here the inductance front end. Normally on the inductance front end, we have a lot of pulses. If you use oscilloscope and you measure here, there's a lot of pulses here, right? So this is the PWM pulse, and on the outside we have a nice high level. On the back end, we have a nice high level voltage of its corresponding voltage outputting, right? And I'm not going to go into the detail of a PWM circuit, so this is not really a PWM circuit class. This is notebook power supply, right? And that's paid. Alright, so this is a demo video. Okay, so as you can see, we have, just go again, we have an upper MOSFET, we have a lower MOSFET, alright, upper and lower. Alright, this is a PWM control chip, and this is a coil, and we have here a filter capacitor. That's it. So that's what all the components that makes up a typical PWM circuit. Alright, let's take a look at another one. As you can see here, we have integrated upper and lower FET PWM circuit. As you can see, we have here a chip, we have a coil, we have the filter capacitors, but we don't see any MOSFETs. So this chip has the MOSFETs integrated inside of it, right? So this is the new power supply PWM chip. On most motherboards, you don't see any upper and lower MOSFET. You just see the only thing you see is the PWM chip and a coil. So the MOSFETs are integrated. But if you measure here with oscilloscope on the front end here, you will see pulses, right? You will see pulses here on the front end, right? And on the output, it's smooth. It's the same technique, the same principle. It doesn't change, just that the MOSFETs are integrated inside of the chip, right? And this is most of the newer models laptops have this power supply delivery using integrated MOSFET upper and lower chip, PWM chip. Alright, and as you can see, a physical appearance of a PWM circuit. So this is the PWM chip here, right? We have two MOSFETs and a coil and a pair of filter capacitors, right? So this is a PWM chip. As you can see, this is normally an upper MOSFET. If you notice this large capacitor here, it's normally 19 volts coming to the drain pins. These 4 pins up here are the drain, and these are the source. The first 3 pins are the source. This is the gate, and the gate is normally connected to the PWM chip for controlling its switching, As you can see, this is another MOSFET, pin number 1, the source. This is normally connected to ground, right, and its gate is also connected to the PWM chip, right, and they are controlled by this PWM chip to output the power. As you can see, this is a coil, right, this is the output coil, and here are the filter capacitors, right. So this is a typical physical appearance of a PWM chip, right. And if there is no schematic, you can use your multimeter to determine which is upper and which is lower. Alright, so let me get over to the camera here. Pause. Alright, so I'm on my webcam here, and I'm going to have here a motherboard. Let me see if I can get the camera up to. Alright, so I have here a board, as you can see. Alright, so here we have 3 coils here, and we have a pair of MOSFETs here, right? So we have the filter capacitors are here, and some are on the back side also. Right, so we have MOSFETs, capacitors, filter capacitors, and the coil. As you can see, it's close to the CPU power supply, so these are going to power the CPU, right, as the integrated graphics supply and the core supply, right. So 2 MOSFETs, upper and lower, a coil and a filter capacitor, and this is the PWM chip here, right. It's the same, right. So to know how to know if this is a upper and lower MOSFET, normally I just use my multimeter and I'll connect my red probe to ground, and I'm going to connect the black probe to the first pin. If it beeps, then this is the source pin. This is a lower MOSFET. See, pin number 1, pin number 2, pin number 3, right, pin number 4, which is the gate. There's no beep. If that's a beep, that's a short circuit. Right, so pin number 1, 2, 3, right. This is the drain, which is connected to the coil. See, it's connected to the coil. Let me zoom in. Let me see if I can zoom in. Alright, so this is the upper MOSFET, and it is connected to the coil. Alright, let me see this MOSFET. Sometimes they use 2 lower MOSFET, yes, because the CPU power supply is so large. The CPU power supply needs 2 MOSFET to switch in, because if you normally use 1 MOSFET and 1 upper and lower MOSFET, the CPU power supply is shared, right? So if the CPU power supply total amount of current is needed is 90 ampere, right, it should be at least 45. 145 ampere should be going to from one phase, because it's connected in parallel. These coils are connected in parallel, so 145, another 45, which is a total of 90 ampere, right? So normally these MOSFET is acting as a shared current, right? That's how they designed it, right? So the PWM circuit of the CPU power supply is very complex, right? This is a class by itself, right? So it is a shared current, so each should give at least 45 ampere, and it's connected in parallel to produce 90 ampere, right? If you go over 90 ampere, then it is over current protection. The chip will, what will happen is that the upper the chip, it has a VR hot pin. What will happen is that if the MOSFET, there's normally a thermistor, which is a NTC, negative thermal coefficient resistor. When the resistance and the temperature increase, its resistance decreases. So it measures the upper MOSFETs, which is on this side. Right, these are the ground MOSFETs. So the upper MOSFET, there's a resistor that is connected. There's a resistor that is connected close to it. On the back side, here it is. This is it. So this resistor is a negative thermal coefficient resistor. if this resistor is faulty, it can cause power down. Let me see if I can. Right, this is the resistor here. If this resistor is faulty, it can cause power down and other abnormal fan spin while and so forth. So this MOSFET needs to be controlled by this PWM chip, and this is the CPU power supply PWM chip controlling the two MOSFETs. Right, if the MOSFET is switching too hard, it becomes hot. So that is why most times they put a thermal pad on these to what? Protect and to control and to keep them cool, right? And then when they switch too hard, what will happen is that when the temperature increases, the resistance of this resistor decreases, and what happens the CPU will, the PWM chip will detect that, and then it releases the VR hot signal to the CPU to drop the frequency. So that is why sometimes the CPU, the computer will be gradually slow because it's dropping its frequency. If there is any fault, if the current is too hot, if the high and the temperature is too high, then what will happen is that there's another NTC resistor. That resistor is going to basically tell the CPU, which is the therm chip pin, to shut down the computer because it's in over temperature, it's too high. Alright, so here are some other MOSFETs, and these MOSFET, which is the drain pin, which is connected to a capacitor here, and this is their upper MOSFET. These are all their upper MOSFET, see, all connected to the 19-volt rail. Alright, the drain pin, they are connected. Alright, so these as you can see here, is their upper MOSFET. This is the drain, this side is the drain, this is the drain, and it's connected to these capacitors. These are filter capacitors, which has the 19 volts. Alright, so let's continue. Alright, so this is a typical PWM circuit. Here's another one. So we have a PWM chip, we have two MOSFETs, a coil and a capacitor. Alright, and here's another one. Alright, so if there's no schematic, you can use the technique that I'll show you to decide which one is upper and which one is lower. Alright, so this is the two MOSFETs, upper and lower MOSFET, and this is a coil and a filter capacitor. Same over here. Right, two MOSFETs, the PWM chip is on the next side, two MOSFET, upper and lower, a coil and a filter capacitor. Alright, so this is the notebook power supply delivery of the PWM, LDO and the switch mode power supply. Alright, this is a demo video. Alright, so as I said, I'm starting Skype online classes one-on-one, right? And if you are group class, so if anyone is interested in Skype online live classes, I will record the classes and upload them, right? So you can download them and have them to watch at your own leisure time, right? And I have placed that information in the community section on my posts. You can check it out, right, for live online Skype classes. All right, so thank you.